be talking about Biot-Savart law in magnetic field and one simple equation of the law, how it applies. Let's think about a very long wires, arbitrary, so carries current I, and some element, we think about some element called TL. TL, and it's the line, we know the magnetic field by right hand rule this way. At some point, think about P, the distance from TL to P we call R, here R. What is the magnetic field P at this point P? TL create TB. TP inversely proportional to R square, proportional to current I, and proportional to the line element TL, and proportional to this theta, sine theta angles, and the direction at this point P is TL multiply TL times the cross product of R direction. R is the unit vector of R, and proportional factor is 4 pi with zeros. This sine theta in direction we can write simply in this vector product notation. This is the Biot-Savart law. The whole form we can write P equal I integral R square TL cross R. Some contour. It's very simple. And practical form, the practical we can write TB equal R square sine theta TL. This gives the magnitude of dB and more practical. This is the Biot-Savart law to find the magnetic field P at this point. Everything is constant. We focus only this part. This part is important. Now let's apply this law, a very typical problem, very typical example. Every electromagnetic book contains these examples. Erase. There's a line element. That line element carries current I, and at point P, for example, P, the distance from the point to line equal A is A, and 2n angle equal theta 1 and theta 2. What is the magnetic field P at this point by this line element? This calculation is very typical problem and very useful. Let's construct one coordinate in this way. Here, this is dx, x from here, this is origin, and we call this as R. Then the magnetic field dP by this dx, we can write in this way: dB equal I R square, and that's defined on angle. This is the theta. Sine pi minus theta. And dx. Right. A is constant, but R and X both are variable. We do not need two variables. We can use only one variable, theta. And if our current flows from the negative infinity to positive infinity, the angle theta moves between these 2 points, pi minus theta 1 to theta 2. If current flows this way, we switch these two end terminal angles, switch that. It's not serious, it doesn't matter anyhow. How to calculate this? We convert R and X just theta. What is sine theta? What is sine theta? Sine theta equal like that. Then R equal A cosecant theta. What is tangent theta? Then x equal A cotangent theta. Then we obtain this dx. dx equal here minus A cosecant square theta. We put this dx and R this equation. Sine theta. What is dx? Minus A cosecant theta d theta. R square A square cosecant square. Beautifully, cosecant square term cancel out. We're happy. And we have only one A. Simple. Now we obtain the total B. The integration is simple. We prepare the more compact form in this way. P equal here. Mu 0 I divided by 2 pi A is common. We know already what it means. And this term, cosine theta 1 and cosine theta 2 divided by 2 is just numerical arithmetic average. This theta. It's beautiful. And special case, what happens if a line is infinitely long? Infinitely long means theta 1, 0, theta 2, 0, both. Infinite long wire means this right term, cosine theta equal 1, cosine theta 2 equal 1. Then the right side is just total 1. Flow equal mu 0 I divided by 2 pi a for infinite large long wires. Some book defines angle in this way. This angle is alpha 1 and then it is alpha 2. The same problem. Then the B equal sine alpha 1 plus sine alpha 2. Just arithmetic average. What do you think about that? It's compact and simple, and this formula is very useful for any arbitrary finite line element.